So this will be our last thing to talk about while we are in our electrodynamics or circuits unit. And this is all about one new element we've mentioned before but haven't really talked about, and that's capacitors. So capacitance is one of the most complicated elements that we'll talk about, but really for what you need to know, it's not going to be too hard. Some things are kind of involved, but none of it is really, impossible to work with. So, really, a lot of it is just knowing, basic principles and nothing super complicated. So, capacitors are devices that store charge. Usually, they're made up of two parallel plates with some kind of space between them. So the plates are going to have an equal and opposite charge on them, and that'll create a potential difference between the plates, in that area between the plates. A capacitor can be made of really any shape, but most of the ones that you'll work with are parallel plate capacitors. That's the most common kind. In circuit diagrams, that's actually how we represent them too, by two parallel lines. So it look like this if it's in a circuit. So we have a battery here, and then these two parallel lines are a capacitor. When we talk about capacitors, the ratio of charge to potential difference is called the capacitance, or just capital C. And since it's a ratio of charge to potential difference, the equation for it will look just like that. So charge over potential difference. C equals Q divided by V. If we have a parallel plate capacitor, then C, the total capacitance, is directly proportional to however big your plates are, so the area of the plates, and inversely proportional to how far apart they are. We'll call that distance D. So say if we double the area of the plates, then we double the capacitance. If we double the distance between the plates, then the capacitance is halved. And there's actually an equation here. I'm not sure why I didn't leave a space for it in the notes, but capacitance is also equal to epsilon naught times the area divided by the distance that separates the plates. So this equation goes with this stuff down here. The unit for capacitance is the farad. You'll probably just see it abbreviated with a capital F. So since it is charge over potential difference, then 1 farad would be the same thing as 1 coulomb per volt. So 1 farad is 1 coulomb per volt. In real life, most capacitors have really small capacitances, and you'll usually see them measured in microfarads, or we could say 1 microfarad. And remember, the prefix micro just means 10 to the minus 6. So a lot more likely you'll see microfarads rather than farads. In a sense, a capacitor can kind of perform the same job that a battery would. So there's some kind of energy associated with moving a small amount of negative charge from the positive plate over to the negative plate of the capacitor. and something has to do that work. And that work is where the energy comes from. So all the energy the capacitor stores comes from something doing the work to separate those charges. So if the plates have a charge of Q, then the potential difference between them would be from that equation we just had, V equals Q divided by C. Just do a little bit of algebra to rearrange our equation. If Q is 0, and the work done to add charge until we build up some bigger charge, capital Q, then the total work required to do that, U, is 1/2 times QV, or Q delta V, you might also see it written. So total amount of energy, or total amount of work to separate those charges and build up all that energy is 1/2 QV. So we can take this equation and the equation we had before for capacitance, which was C equals Q over V, and we can actually express the energy in a few different ways. So one of them, let's say we take the equation as it is solved for V, and we plug in for V, then we'll have 1/2 Q squared divided by C. So 1/2 Q squared divided by C. Another way we could express it is by solving for Q. So Q would be C times V, which would give us 1/2 CV squared. Or we could just leave it in that form up above, 1/2 Q times V. So 3 different ways, depending on what information we have, to talk about the energy associated with some arrangement of charge in a capacitor. So just like when we studied resistors, we can arrange capacitors in series or parallel as well. It's just that the math associated with doing that is actually backwards. So the rule when we add capacitors in series is that they act like resistors in parallel. And then for capacitors in parallel, those add like resistors in series. So what does that mean? If we have 2 capacitors in series, so run one right after each other in a line, then our equivalent capacitance is going to be how we do the inverses for resistors. So 1 over our equivalent resistance is going to be equal to 1 over capacitor 1 plus 1 over the capacitance of capacitor 2, so on and so forth until you get all the way up to your nth capacitor. And then when they're in parallel, they do the opposite of resistors in parallel. So here, our equivalent capacitance is just, C1 plus C2 plus all the way up until you hit your very last capacitor. Okay, so let's try that out here. We have this arrangement of capacitors. We know C1 is 2 microfarads, C2 is 6 microfarads, C3 is 3 microfarads. What is the total capacitance in the figure above? So we're jumping right into combination thing. Parallel part before we can start adding the series. So what is the equivalent of 1 and 2? Well, since they're in parallel, we just add them together. So it would be C1 plus C2. So that's just going to be, let's see, 2 microfarads plus 6 microfarads. So altogether we have 8 microfarads in that parallel section. Alright, so now that we have this simplified to just one equivalent capacitor, we can add C1 and 2 to C3 since now they're in series. So our overall equivalent capacitance is just the inverse of the sum of the inverses. So 1 over 8 microfarads plus, what was 3? 1 over 3 microfarads, and then we invert that. So 1/8 plus 1/3, that's 11 over 24. Probably looking at about 2.18 microfarads for the total capacitance. So almost done with this unit. Last thing to talk about is how do we get these plates to stay apart? And that's where dielectrics come in. So one way to keep the plates of a capacitor apart is to put some kind of insulator between them, and that's called a dielectric. So a dielectric actually increases the capacitance. When we put an insulator in between, we increase the capacitance. So between the plates of the capacitor, there's an electric field buildup. We have positive charges on one plate, negative on the other, and it creates an electric field between them. So the field polarizes all the molecules that you have in a dielectric. So some of the electrons in the molecule move to one end, and then the positives move down toward the other end. You can see that in this picture a bit, how they're all lined up with negatives on top, positives on the bottom. Alright, great. So all the molecules line up. How does that help? Well, that movement of electrons creates a layer. You can see this whole top row is just a layer of negative charge right by the positive plate. And we have a layer of positive charge right by the negative plate. So that separation of charges creates another electric field. And it goes in the opposite direction. So it reduces the total electric field. So if we wanted to calculate what's the new electric field, well, we would just have whatever our old one was minus the induced electric field from the alignment of charges in our dielectric. And that's just going to be E divided by, gotta get a. Alright, so electric field divided by kappa. It looks like a little k. So that Greek letter, kappa, it's called kappa, but more importantly, for what we're learning here, that's called the dielectric constant. And every material is going to have its own, but more importantly, for all materials, what they all have in common is that the dielectric constant is bigger than 1. So really, it's more like it's just a ratio of electric fields. Alright, so we can shrink an electric field. It seems counterintuitive that that would be something that helps, right? But for a parallel plate capacitor, that reduction in the electric field means the potential difference is also reduced. So we have here since we can talk about capacitance in terms of charge and potential difference, we could say that our new capacitance is equal to kappa multiplied by our old capacitance. So if we're decreasing the potential difference, since capacitance, remember, is equal to Q divided by V, if we decrease this V, then our capacitance is going to shoot up. So last little tidbit about capacitors. If you have a potential difference across a capacitor that's too big, then the electric field is so strong that the electrons are actually able to jump off of their atoms and move across to the other plate. That's called a dielectric breakdown, and it completely discharges your capacitor, so you lose all the energy you have stored in it. So that's one bad thing. But another bad thing is that with all those high energy electrons jumping from one plate to the other, you could burn a hole in whatever dielectric material is separating the plates and completely ruin the capacitor.